You know, even the smartest engineers can just get the numbers wrong, and when they do, the results are terrifying. From bridges that shake and wobble to scorching building reflections that roast everything in their path. Join me for today's video. We're going to look at 15 times engineers used the wrong math. Number 15. The Millennium Bridge. London's Millennium Bridge, a pedestrian-only steel suspension bridge that crosses the River Thames, opened to great fanfare on June 10, 2000. It was the first new bridge to be built across the river in more than a century and was expected to be a modern architectural landmark. Instead, it quickly earned the nickname the Wobbly Bridge when it began swaying unexpectedly just hours after opening. The cause? Engineers had underestimated how pedestrians walking in unison could induce lateral resonance. This is an error in understanding dynamic loading and crowd behavior. The bridge was originally envisioned as a sleek, minimalist structure with suspension cables below the deck to preserve an uncluttered view. But shortly after the public stepped onto the bridge, it began to sway from side to side in a way that made walking uncomfortable and, for some, disorienting. The oscillation grew worse as more people tried to cross. The phenomenon was not the result of a structural failure. The bridge wasn't in danger of any collapse and all components were functioning as designed. The real issue was a little-known effect called synchronous lateral excitation. As people walk across, they naturally adjust their gait to match the small sideways motions of the bridge. This synchronization amplified the sway, creating a feedback loop where the bridge moved more, prompting pedestrians to align further and increasing the motion again. This kind of resonance had been observed before but was rarely studied in depth, and certainly not to the degree experienced on the Millennium Bridge. Engineers quickly realized the seriousness of the issue and closed the bridge just 2 days after opening it. It remained shut for nearly 2 years while a solution was developed. The fix involved retrofitting the bridge with a series of tuned mass dampers and viscous fluid dampers. These are devices that absorb motion and dissipate the energy. These additions were installed underneath the deck, preserving the bridge's aesthetic. And when the bridge reopened in 2002, the swaying was gone, and it's since become a popular pedestrian route between the Tate Modern and St. Paul's Cathedral. This incident, however, became a high-profile example of how even advanced engineering firms can just overlook crucial dynamic behavior. The bridge episode has now become a textbook example in structural dynamics. It spurred more research into how foot traffic affects bridges, and it's influenced the design of similar structures around the world. It shows how even small errors in dynamic calculations, especially those involving humans, can lead to embarrassing and costly outcomes. Number 14. The Vasa warship, Sweden's floating miscalculation. In 1628, the Swedish Royal Navy launched what was intended to be one of the most powerful warships in Europe, the Vasa. Constructed on orders from King Gustavus Adolphus, the Vasa was meant to project Swedish naval dominance during a period of regional conflict and military ambition. It was lavishly decorated. It carried 64 bronze cannons and stretched over 69 meters long, but it sank less than a mile into its maiden voyage, largely because its builders got the math wrong. Now, the cause of this disaster lay in the ship's stability, or rather lack of it. The ship was dangerously top-heavy, with insufficient ballast to counteract the weight of its upper structure and artillery. Naval engineering in the early 17th century was more art than science, and shipbuilders relied heavily on experience and scaling up previous designs. Unfortunately, in this case, the addition of an extra gun deck, ordered during construction, fundamentally altered the vessel's center of gravity. During a test where 30 men ran side to side across the deck to simulate wind-induced tilting, the ship began to rock alarmingly. The test was stopped before completion for the fear ship would capsize right there at the pier. Despite this red flag, though, it was launched as scheduled. One key issue was that shipbuilders of the era lacked any standardized mathematical tools for calculating a ship's metacentric height. That's an indicator of how stable a vessel would be when tilted. Modern engineers used well-established formulas involving weight distribution, center of gravity, and hull shape to model stability accurately. In the 1600s, though, such quantitative methods were not widely applied. The Vasa's builders misjudged how much ballast was needed and how high the center of gravity would be once the upper decks and cannons were in place. When the Vasa encountered a modest gust of wind shortly after setting sail, it heeled sharply, water poured into the open gun ports, and the ship capsized in Stockholm Harbor. Although human casualties happened, the focus here is on the engineering missteps rather than the loss of life. Remarkably, the Vasa was salvaged in the 1960s, and it's now housed in a museum bearing its name in Stockholm. Analysis of the ship's remains has confirmed that its instability was a consequence of flawed weight distribution. The Vasa remains one of the best preserved examples of a 17th century warship, and one of the clearest examples in history of how engineering intuition, when unaccompanied by sound calculations, can quite literally sink a project. Number 13. The Patriot Missile failure of the Gulf War in 1991. 1991. During the Gulf War, the U.S. Army Patriot Missile defense system was deployed to intercept Iraqi Scud missiles. The Patriots were promoted as highly accurate and technologically advanced, designed to detect, track, and destroy incoming ballistic threats. However, a serious mathematical flaw in the software's internal clock calculations caused a failure that led to at least one well-documented incident where a Scud missile was not intercepted. The core of the issue lay in the way that the Patriot system tracked time. The system's internal clock measured time in tenths of a second and stored that value as a 24-bit binary number. To convert this time value into seconds for use in floating-point arithmetic calculations, the software multiplied the stored number by a fixed decimal approximation of 1/10. That's 0.1. However, 0.1 cannot be represented exactly in binary floating point, just like 1/3 can't be expressed exactly in decimal. As a result, every time conversion introduced a tiny rounding error. This error was minuscule. It's on the order of something like 0.00000095 seconds per operation, but it accumulated over time, and after the system had been running for many hours without a reset, over 100 continuous hours in one case, the total timing drift became significant. The system's calculated position of the Scud missile no longer matched its actual trajectory. When the Scud entered the Patriot detection zone, the system misjudged its location by several hundred meters, enough to cause the intercept attempt to fail. After the incident, an investigation found that the software error had been known prior to deployment, but it was considered too small to affect performance. It was only under real-world wartime conditions, which is 24/7 operation, that drift became meaningful. In the aftermath, software patches were issued to reset the system's clock periodically, and mathematical error was corrected in future versions of the Patriot system. But the lesson from this failure was clear. In high-precision real-time systems, even microscopic rounding errors can lead to failure if allowed to accumulate unchecked. It shows how even a well-designed system can fail due to an unanticipated accumulation of floating-point errors, a technical but very real example of the wrong math being used in the wrong way at the worst possible time. Number 12. The Hubble Space Telescope, a spherical aberration error. Launched in April of 1990, the Hubble Space Telescope, it was one of NASA's most ambitious instruments. It was designed to deliver unprecedented clarity in space-based observations. Hubble was expected to revolutionize astronomy. But when the first images were returned to Earth, scientists were stunned to find that the telescope's pictures were blurry, far from the crisp clarity that had been promised. The cause? A critical mathematical error in the shaping of the primary mirror. The primary mirror of Hubble was manufactured with precision. The specifications called for a curvature accurate to within 10 nanometers. However, the mirror ended up being off by about 2,200 nanometers. That's 2.2 microns. That's an astonishingly small error in human terms, but it's catastrophic for the telescope's ability to focus light. This introduced a flaw known as spherical aberration, where the light reflecting off the outer edges of the mirror focused at a slightly different point than light from the center, resulting in blurry, unfocused images. Now, the root of the problem traced back to a testing device called a null corrector, which was used to guide the grinding of the mirror's shape. During final assembly, the engineers at the contractor Perkin-Elmer replaced a lens inside the test device slightly out of position by just 1.3 millimeters. That small misalignment caused the device to give a false green light that the mirror had been shaped correctly, when in fact it had not. The worst part? The other independent testing equipment at the time indicated something was wrong, but those results were ignored in favor of the faulty test. The consequences were severe. NASA had already spent over $1.5 billion on the Hubble project, and a replacement mirror was not feasible. The telescope was already in orbit, 550 kilometers above the Earth. The only solution was to send astronauts to install a corrective optics package, essentially giving Hubble a pair of glasses to counteract the flaw. In December of 1993, the Space Shuttle Endeavour carried a team of astronauts on the first Hubble servicing mission. They installed the Corrective Optics Space Telescope Axial Replacement, or COSTAR, and they replaced key components with adjusted optics. The mission was a huge success, and the corrected images from Hubble began to fulfill the telescope's original purpose, delivering jaw-dropping views of distant galaxies, nebulae, and black holes. The Hubble case highlights the critical importance of independent verification in engineering. Even when tests seem to confirm a result, redundant systems and contrary data must not be dismissed. It's a clear example of how flawless execution of flawed instructions can still yield failure, proof that the right tools with the wrong math still leads to the wrong results. Number 11. The Hyatt Regency Walkway Collapse. The Hyatt Regency Hotel in Kansas City, Missouri. It opened in 1980 with an architectural feature that was pretty striking: a large atrium spanned by several elevated walkways suspended from the ceiling. These skywalks allowed guests to look down on the lobby area from above, creating a dramatic visual effect. However, just 1 year later, on July 17, 1981, two of the walkways collapsed during a crowded event. While the incident tragically involved the loss of life, we're going to focus strictly on the mathematical and design error that caused the failure, not the human consequence. The problem originated in the way that the walkways were suspended. The original design called for a single set of continuous steel rods running from the ceiling down through the upper skywalk to the lower one. This meant that the load from both walkways would be transferred through a single rod system, allowing the stress on each rod to be calculated and managed. However, during construction, a seemingly minor change was made to simplify fabrication. Instead of using a single continuous rod, the builder proposed using two sets of rods, one from the ceiling to the upper walkway and another from the upper walkway to the lower. While this change may have seemed minor in physical layout, it doubled the load on the connectors supporting the upper walkway. The original design placed about 60% of the total load on the ceiling supports and 40% on the walkway joints, but this new configuration shifted the full weight of the lower walkway directly onto the upper one's connections. The connections were not redesigned to accommodate for the increased load, and as a result, the structural components were operating well beyond their safety limits. Now, the mathematical failure here wasn't an arithmetic mistake, but a misinterpretation of how a structural change would redistribute forces. That's a core part of civil engineering calculation. The new rod configuration introduced an unintended load path, changing the magnitude of the force acting on some critical components. Unfortunately, neither the engineering firm nor the contractors ran a new structural analysis after the change, and the oversight led to one of the most cited design miscalculations in modern civil engineering. Following the collapse, extensive investigations by the National Bureau of Standards revealed that the failed connections had only about 30% of the strength required to support the actual loads they experienced. Engineers had not recalculated or validated the revised design against known load-bearing formulas or even safety factors. As a result, major changes were introduced into engineering practice in the United States, including stricter design review process, clearer delineation of responsibility between designers and fabricators, and more rigorous building code enforcement. The American Society of Civil Engineers continues to use this example in ethics and design training programs. It shows the necessity of reassessing all calculations when any part of a load-bearing system is altered, even slightly. Number 10. The Gimly Glider, the metric conversion mishap. On July 23, 1983, an Air Canada Boeing 767 was en route from Montreal to Edmonton when it ran out of fuel at 41,000 feet. The pilots managed to glide the unpowered aircraft nearly 80 miles and land it safely at a former Royal Canadian Air Force base in Gimli, Manitoba, a remarkable feat of airmanship that earned the aircraft the nickname the Gimly Glider. At the time, Air Canada was transitioning from imperial to metric measurements, and the Boeing 767 was the airline's first aircraft to be fully equipped with metric fuel systems. However, during the refueling process, the ground crew used pounds instead of kilograms when entering the density factor needed to calculate fuel volume. The aircraft needed about 22,300 kilograms of fuel for the flight. Instead of using the correct conversion factor at 1.77 pounds per liter, the crew mistakenly used 0.8, converting pounds to liters as if they were kilograms, and severely underfueling the craft. The error went undetected because both the pilots and the ground crew assumed the math had already been verified by the other party. Compounding the issue was the fact that the flight computer accepted the input without alerting to any anomaly. The aircraft departed Montreal without sufficient fuel, and it completed more than halfway the journey before both engines failed due to fuel starvation. When the engine stopped, the plane lost all thrust-generated electrical and hydraulic systems. However, the Boeing 767 was equipped with a ram air turbine that deployed automatically to provide minimal power for essential flight controls. Fortunately, the pilot, Captain Robert Pearson, had gliding experience from flying sailplanes, and First Officer Maurice Quintal recalled an abandoned airstrip at Gimli that could potentially serve as a landing site. Remarkably, they managed to glide the aircraft down and land safely, though not without incident. The airstrip was being used for a go-kart race at the time. After the incident, investigations by Canada's aviation authorities confirmed that the incorrect fuel density conversion was the root cause of the problem. The event did help accelerate the global aviation industry's shift towards more consistent use of metric units and redundant systems checks. The Gimli Glider incident is now a staple example in engineering and aviation training. Thankfully, this time, the math error didn't end in disaster, but it came close. Number 9. The Lotus 123 spreadsheet bug. In the 1980s and early 90s, Lotus 123 was one of the most popular spreadsheet applications in the world, used by millions of businesses, accountants, and analysts. But a seemingly minor math error embedded in its programming led to significant issues for users relying on precise calculations, particularly those involving dates, timekeeping, and financial data. The problem? Integer rounding in the spreadsheet's handling of dates caused incorrect outputs in a number of real-world applications, sometimes going unnoticed for years. The core of the error revolved around how Lotus 123 handled date values. In spreadsheets, dates are typically stored as serial numbers. For example, January 1st, 1900 is represented as 1, and each subsequent day increases that value by 1. However, Lotus 123 incorrectly assumed that the year 1900 was a leap year, and therefore allocated an extra day, February 29th, 1900, which didn't actually exist. This introduced a one-day shift in all serial date calculations from that point forward. Now, while that error might seem trivial, it had ripple effects. Financial models relying on accurate compounding over time, interest rate projections, loan amortization tables, and payroll systems could all be thrown off by the misalignment. A miscalculation of even a single day could result in incorrect accrued interest or misdated transactions, particularly over long time spans. To make matters worse, Lotus handled large numerical values with limited precision in some cases. For instance, when performing calculations with very large integers, rounding errors could happen due to limitations in how many significant digits the program could store. In financial systems, where even a difference of a few cents could have regulatory implications, these discrepancies were enough to prompt concern from auditors and software reviewers. By the time the leap year mistake was identified, a huge number of spreadsheets and financial templates were already in use that had compensated for the issue, either manually or unknowingly. Correcting the bug would have caused older spreadsheets to yield different results, possibly disrupting business logic that users had come to rely on. As a result, the developers chose to keep the bug to preserve consistency. Microsoft Excel later duplicated the same erroneous leap year to maintain compatibility with the Lotus 123 files, and to this day, most spreadsheet programs treat 1900 as a leap year for the sake of legacy file compatibility. The persistence of this error across the decades of software development shows how deeply flawed math, once embedded, can become institutionalized. The Lotus 123 bug didn't cause any visible crashes or hardware failures. It simply produced subtly wrong results, and that's what makes it so insidious. It's a reminder that in software engineering, close enough is not good enough when it comes to math. Number 8. The Mars Climate Orbiter. In 1999, NASA lost contact with its Mars Climate Orbiter just as it was about to enter the Martian atmosphere. The mission, valued at about $327 million, was intended to study the Martian climate and serve as a relay station for the Mars polar lander. Instead, the spacecraft burned up or skipped off the atmosphere entirely due to one of the most avoidable errors in aerospace history, a simple unit conversion mistake. At the heart of the failure was a miscommunication between two teams working on the mission. The spacecraft was built by Lockheed Martin, whose engineers used imperial units, specifically pound-seconds, for force measurements. NASA's Jet Propulsion Laboratory, JPL, however, operated using the metric system and expected those values in Newton seconds. When trajectory correction maneuvers were calculated, the navigation software misinterpreted the data due to the inconsistency in units. The discrepancy resulted in the orbiter approaching Mars at an altitude of 57 kilometers instead of the intended 140 kilometers, way too low for the fragile probe to even survive. What makes this case notable isn't just the math error itself, but the systems-level oversight failure that allowed it to persist. Multiple simulation runs and checks should have revealed the anomaly in the trajectory, but none of the teams caught the problem in time. Post-mortem results by NASA noted that the lack of cross-checking, limited communication between teams, and failure to implement software validation tools all contributed to the loss. The fallout led to significant changes in how NASA manages software verification. The agency revised its standards for documentation, added redundant checks, and mandated that all contractors use the metric system. While the incident was a blow to NASA's reputation, it did offer a lesson in the importance of unit consistency. The orbiter has since become a textbook case in engineering and project management courses, showing how even highly technical billion-dollar efforts can falter due to fundamental math misunderstandings. Moving on to number 7, the Ariane 5 Flight 501. On June 4, 1996, the European Space Agency, or ESA, launched its new Ariane 5 rocket for the first time. It was designed to carry heavier payloads into space than its predecessor, the Ariane 4. This launch was highly anticipated, but just 37 seconds after liftoff, Ariane 5 veered off course, broke apart, and self-destructed. This wasn't a structural failure or an engine malfunction. It was a simple software error rooted in a mathematical assumption that no longer applied to the new rocket's performance. The core of the problem lay in the rocket's onboard inertial reference system, that's IRS, which measured the vehicle's orientation and position in flight. This system used software adapted from the Ariane 4 program, which had a slower launch trajectory. A key part of the software converted a 64-bit floating point number, representing the rocket's horizontal velocity, into a 16-bit signed integer. On Ariane 4, the velocity never exceeded the range that the 16-bit integer could represent, but Ariane 5 accelerated much faster. During its maiden launch, the velocity exceeded the upper limit of 32,768, the maximum positive value for a 16-bit signed integer. This caused an overflow error. When the error happened, the IRS shut down and passed control to a redundant backup system. But the backup system was running the same flawed software and failed in exactly the same way. With both systems offline, the guidance computer began receiving nonsensical data, and it responded by making incorrect course corrections. These erratic commands caused the rocket to break apart under aerodynamic stress. The loss was estimated at over $350 million, making it one of the most expensive software bugs in history. A post-failure inquiry found that the software module responsible for the error was not essential to the flight. It had been kept in the system purely for legacy reasons, and the engineers never anticipated that it would be exposed to a velocity higher than had been in Ariane 4 launches. The Ariane 5 failure is now a classic case study in software engineering. Never reuse software in a new environment without thorough testing. Always implement robust exception handling, and, more importantly, ensure that the range and conditions of operations are validated against real-world use cases. After the incident, the software was completely rewritten and extensively tested. Ariane 5 went on to become one of ESA's most successful launch vehicles, completing dozens of missions with high reliability. But the inaugural failure is a stark example of how a simple mathematical oversight, specifically an assumption about numerical range, can derail an otherwise solid engineering design. Number 6. Denver International Airport's baggage system. When Denver International Airport opened in the mid-1990s, it was hailed as the most advanced airport in the United States. A key feature meant to support this claim was an automated baggage handling system designed to transport luggage seamlessly between terminals, check-in, and aircraft. The concept was ambitious. Multiple underground conveyor lines, laser scanners for sorting, and robotic carts would replace traditional manual baggage handling, saving time and money. But what actually happened became a modern parable of engineering misjudgment and software overreach. At the core of the failure were incorrect assumptions and flawed estimates about timing, logistics, and system integration. Planners underestimated how quickly baggage carts would need to load, route, and deliver luggage. For example, calculations projected that individual pieces of luggage could be processed in seconds and routed without any significant delay. In reality, bag jam frequencies, cart collisions, and misreads at scanners added seconds and then minutes to the total flow. These small discrepancies weren't just annoyances, they completely disrupted the flow model on the system. One of the main missteps was that engineers assumed an ideal operating environment and used the best-case data rather than the average or worst-case conditions without estimating throughput. Software limitations based on those optimistic models failed to capture what would have happened when multiple variables, like early or late arrivals, misplaced bags, or rerouted flights, interacted simultaneously. But beyond the timing issues, there were poor decisions in physical design. Conveyor tracks were too narrow in some sections and too steep in others, leading to frequent jams. Mechanical systems were not robust enough to handle real-world variations in bag weight and size, and furthermore, the software had no adequate error recovery. Eventually, the opening was delayed about 16 months, and the project went over budget by about $560 million. Most of the automated system was quietly abandoned. In the end, the airport reverted to traditional manual handling in most terminals. This failure wasn't due to one major flaw, but rather a buildup of underestimated variables. The baggage system here is now widely studied as a case study in engineering and project management circles, showing how overly idealized models and poor error handling can doom even the most high-tech designs. Number 5. Vancouvers Point Gray wastewater tank. In the early 1970s, the city of Vancouver undertook an infrastructure project to upgrade its wastewater treatment capacity near the Point Gray area. A critical component was the construction of a large circular concrete tank intended to store and manage overflow. The design appeared simple and well understood. Pour reinforced concrete into a cylindrical shape, install plumbing and support systems, and then seal it for regular use. But shortly after the tanks were completed and filled, large cracks appeared. Water seeped through and entire sections of the tank required rebuilding. The culprit? A miscalculation in the stress loads placed on curved concrete structures. Unlike flat surfaces, curved walls like those in circular tanks are subject to hoop stress. That's tension that pulls along the circumference as water pressure presses outwards from the inside. Engineers are well aware of this, and there are established equations for calculating the required thickness and reinforcement of curved walls under pressure. But in this case, either the correct formulas weren't used or they were applied under unrealistic assumptions. Records from the failure investigation indicated that the tank walls were designed based on simplified estimates of hydrostatic pressure. In reality, the concrete itself plays a major role in resisting pressure when correctly reinforced and adequately thick. The designers didn't properly calculate the increase in force at the tank's base compared to the top. Water, after all, exerts pressure that increases linearly with depth, so while the upper tank walls were within tolerance, the lower walls were way too thin to resist the greater force. The result was structural cracking along several points. Once cracks appeared, they acted as a weakness, allowing water to penetrate and compromising the surrounding material. Repair costs and project delays ran into the millions, and it was really frustrating for a utility system meant to be low profile and maintenance-free for decades. Engineers learned an important lesson. When working with pressurized fluids and curved walls, precision matters, and geometric effects can't be rounded off or estimated away. The Point Gray incident is now a reference in structural engineering education to show how even standard materials like concrete, when misapplied or misunderstood, can lead to avoidable failure. Number 4. The Sydney Opera House shells. The Sydney Opera House, it is one of the most iconic landmarks in the world. It's admired for its sweeping shell-like design and perched on the edge of Sydney Harbor. But behind that elegant appearance lies a story of extreme engineering difficulty, cost overruns, and especially mathematical miscalculations. The structure's most defining feature, those curved roof sails, caused years of delay, and they triggered a redesign process so intensive that it redefined how architects and engineers approach complex geometry. Originally estimated to take 4 years and cost around 7 million Australian dollars, the Opera House ultimately took 14 years to build, and it cost over 100 million Australian dollars. A major reason for this dramatic shift was that the roof design, proposed by Danish architect Jorn Utzon, looked beautiful on paper, but wasn't easily buildable in reality. The shells were envisioned as a series of freeform curves, organic shapes that had no straightforward geometric representation. At the time, in the late 1950s and early 60s, engineering software and computational tools simply didn't exist to even analyze or simulate the forces acting on these shapes. The early calculations assumed that the roof shells could be constructed as parabolic sections. Engineers tried to work from two-dimensional drawings and translated them into structural components. Unfortunately, these assumptions turned out to be flawed. The complex geometry didn't distribute structural loads in the ways engineers expected. Some parts were under enormous tension, while the others were more fragile than anticipated. To make matters worse, it was discovered that the shells would need massive steel reinforcements to keep them stable, something that hadn't been included in the initial weight or cost calculations. The math problem here wasn't just geometry, it extended into materials and loads. As designs progressed, engineers found they had no accurate way to predict the load path through the shell. Each shell segment made of precast concrete ribs and panels would behave differently depending on the exact curvature. These calculations needed to be solved through thousands of iterations, something that at the time required physical modeling and laborious trial and error. But the Opera House was completed in 1973, years after Utzon had left the project under political pressure. While the final result is visually stunning and celebrated as a feat of design, the process behind it was marred by incorrect assumptions, limited tools, and deeply complex math. Today, the Opera House stands as not only a World Heritage Site, but also a textbook example in architectural circles of what happens when bold design outpaces available computational methods. It reminds engineers that solving geometry isn't just about aesthetics, it's a make-or-break factor in whether something can be built at all. Number 3. The Aloha Stadium Roof Design. Opened in 1975, boy, a lot of stuff in the 70s, Aloha Stadium in Honolulu, Hawaii was designed to be the state's largest and most flexible sporting venue. At the time, it was a symbol of forward-thinking engineering, particularly due to the modular steel roof design. But despite its innovation, the stadium encountered severe maintenance issues much earlier than expected, due in large part to miscalculations involving the climate, materials, and corrosion resistance. The stadium's roof was made entirely of steel, a material commonly used in stadiums across the mainland United States. The designers used standard calculations and load-bearing formulas suitable for environments with relatively dry or temperate climates. However, they didn't account for the specific condition of Hawaii's tropical environment, especially in the salt-laden air from the Pacific Ocean. Steel structures near the ocean are really vulnerable to corrosion, and the rate of decay can be significantly higher in a place like Honolulu, where the humidity and salt exposure are a constant year-round threat. The original design did include anti-corrosion coatings, but these were based on standard applicable rates to inland or mild coastal regions. Engineers underestimated the actual rate of oxidation and material degradation in the Hawaiian setting. Within a few years of opening, the stadium showed visible signs of rust and weakening in its roof supports and structural joints. Some sections had to be closed so engineers could reassess the roof's load-bearing integrity, and investigations revealed that while the initial strength calculations were sound in theory, they hadn't factored in the accelerated rate of wear and tear from the local environment. By the 1990s, maintenance costs for the stadium had ballooned. Entire portions of the roof had to be replaced or reinforced, and over time, the stadium lost its original modular functionality because it became too risky and expensive to move the seating sections. While no catastrophic failure happened, the project does serve as a cautionary tale. They misjudged the role that local climate could play in long-term performance, and in this sense, the math was incomplete. It failed to model reality. In 2023, plans were announced to demolish and replace Aloha Stadium entirely. The new venue will be built using updated materials with corrosion resistance as a central design priority. Number 2. The Tacoma Narrows Bridge. On November 7, 1940, a bridge collapsed in a way that would redefine the understanding of structural engineering for decades. Known affectionately and ominously as Galloping Gertie, the Tacoma Narrows Bridge in Washington state had been open for only 4 months before it twisted itself into pieces and dropped into the chilly waters of Puget Sound. The disaster was spectacular. It was caught on film, and it became a symbol of not engineering incompetence, but of engineering incompleteness. The math wasn't wrong in the traditional sense. The numbers added up, but the models behind the numbers failed to capture the forces at play. It was a mistake in how engineers understood the natural world and how they translated it into formulas, materials, and steel. The bridge was intended to connect the city of Tacoma to the Kitsap Peninsula, reducing travel time and fostering some economic development. In 1938, after years of political wrangling and planning, construction began on what would be the third longest suspension bridge of the world at the time, surpassed only by the Golden Gate and the George Washington bridges. The main span was over 2,800 feet long, and it was designed by engineer Leon Mosev. His vision for the Tacoma Narrows Bridge emphasized minimalism, elegance, and economy. It was structurally daring, and therein lay the problem. Traditional suspension bridges use deep trusses underneath the roadway deck to provide stiffness and resist vertical and torsional movement. Mosev, seeking to reduce weight and cost, opted instead for a shallow plate girder just 8 feet deep to support the bridge's roadbed. This did reduce the overall weight, but it also reduced the stiffness of the structure. The final design was narrow, 39 feet wide, and extremely flexible. These choices weren't made haphazardly. They were based on the engineering knowledge of the time, which relied heavily on static load calculations and simplified assumptions about wind load. The math made sense. The bridge, on paper, was safe. But from the moment it opened in July of 1940, the bridge exhibited some strange behavior. Motorists reported an unsettling rolling motion, as though the deck were riding invisible waves. Workers and drivers nicknamed it Galloping Gertie, and engineers were aware of the motion and sought to mitigate it with the installation of hydraulic dampers and cable stays. At the time, engineers didn't yet have the tools or theoretical framework to predict these complex dynamic behaviors. Wind loads were generally treated as static forces, and the idea that steady, laminar wind could induce a violent oscillating motion wasn't widely accepted. The calculations were correct, within the assumptions of their models, but the models were missing something critical. On the morning of November 7, 1940, the wind speeds around 40 miles an hour, the bridge entered into a dramatic torsional oscillation. The deck twisted up and down violently, with 2 sides of the bridge undulating in opposite directions. The motion intensified until just before 11 a.m. The center span broke apart and fell into Puget Sound. Despite the spectacle, no human lives were lost, although a single car was stranded on the bridge. And a Cocker Spaniel named Tubby, left inside the vehicle, tragically perished when the bridge collapsed. The disaster led to the development of wind tunnel testing for bridges, the adoption of dynamic analysis in structural engineering, and the creation of new design codes that incorporated aeroelasticity. A new science of wind engineering had emerged, focused on the interaction between moving air and large, flexible structures. Subsequent bridges like the Verrazano Narrows Bridge in New York and the Humber Bridge in the UK were tested extensively in wind tunnels before construction, and their designs included aerodynamic shaping to reduce any lift. Interestingly, the bridge that replaced the Tacoma Narrows, completed in 1950, did incorporate lessons learned from the original failure. It was built with deep trusses, better damping mechanisms, and extensive wind tunnel testing. A second parallel span was completed in 2007 to accommodate increased traffic, and both bridges serve as part of State Route 16. In retrospect, the bridge's collapse was kind of like a scientific gift. It happened at a time when engineering as a discipline was transforming from empirical tradition to a more rigorous physics-based science. It exposed a gap in understanding, and it provided a highly visible reason to fill that gap. The equations developed in the wake of the collapse now live in textbooks and simulation software, and hopefully prevent any similar disasters from recurring. Number 1. The Vidara Hotel Death Ray, a calculated reflection that got too hot. When the Vidara Hotel and Spa opened in Las Vegas in 2009, the sleek, curved design immediately drew attention. Sitting within the city center complex, the 57-story building featured a beautiful concave glass facade designed to give guests a sweeping view of the Las Vegas Strip. But shortly after opening, an unintentional engineering surprise began to appear, one that no one had fully anticipated. Certain spots around the hotel's pool deck were getting incredibly hot during the day, hot enough to melt plastic and make metal lounge chairs painful to touch. The cause? A phenomenon that came to be known as the Vidara death ray. The source of the issue was the building's concave design and the way that it reflected the sunlight. Engineers and architects had intended the facade to be both aesthetic and functional, and the glass was used in the building was highly reflective, designed to reduce heat gain inside the hotel. That's good for interior climate control, but with the building's gentle inward curve and angled windows, this reflection was being focused into a narrow moving zone on the pool deck, creating a literal solar hotspot. The phenomenon wasn't the result of a single calculation gone wrong. The engineers had correctly modeled the building for conventional concerns like wind loads, weight distribution, and interior lighting. But what they overlooked was the geometry of the parabolic reflection. When the sun was at a certain angle, especially mid-afternoon, the building acted like a giant mirror concentrating solar rays into zones. Some guests reported burned hair or hot plastic drink cups warping or melting before being left on lounge chairs. The mistake was subtle, but it was significant. While standard architectural models accounted for the sunlight direction and heating in general, they didn't simulate focused sunlight created by a concave reflective surface. So to mitigate the problem, the hotel installed large, non-reflective shade structures and began using specially designed umbrellas to shield the affected zones. They also applied a surface treatment to the glass to diffuse light and reduce reflectivity. And while the issue was resolved relatively quickly and caused no harm, it became a viral sensation and a humorous cautionary tale in engineering circles. The death ray? It wasn't a catastrophic failure. It was an engineering blind spot. Buildings don't exist in a vacuum. They live in the sun, and the wind, and the daily lives of the people who use them. The Vidara incident is now often cited in architecture courses, and for engineers, it serves as a reminder. Sometimes math errors aren't numerical, they're conceptual. You can do the right math and still get the results very, very wrong.